Hi there, folks. Welcome to what's perhaps the very first calculus video you might ever watch in this series. I decided to make a kind of a useful video that I thought would help students understand what calculus is, kind of just at a glance. We're not going to go super detailed into any of these concepts, but it will give you a nice, really cursory glance at the kinds of things you can expect to learn in a calculus class. So I feel like I want to start by maybe identifying the areas that you want to have down really solid before you can begin studying calculus. So as I keep saying in my previous videos, learning math is like building a house. If you build a house with no foundation, the whole thing is going to crumble apart. So you have to have a really strong, a really sturdy foundation in order to effectively learn this material. But what does that mean in terms of calculus and in terms of math? So you might have heard the expression, you have to crawl before you can walk. That applies really, really well in this situation as well. You have to learn basic arithmetic before we learn algebra, for instance. We have to know Algebra 1 before we learn Algebra 2 and pre-calc, and we have to have a really, really solid understanding of basically everything up to calculus. For us to understand calculus really well, not only to understand the operations in calculus, but to understand intuitively what they are and why they are the way they are. So I want to provide just a brief introduction of the main things we can expect to learn in a calculus class. So calculus deals with what's considered to be maybe 3 or 4 different main ideas, depending on who you ask. So one of these ideas is something that's sometimes taught in a pre-calculus class, but other times you may not encounter it until you take calculus for the very first time, and that would be the concept of a limit. So let's start with limits as one of our first main big ideas of a calculus class. What is a limit exactly? I'm so glad you asked. So a limit is a way of describing function behavior where we may not have exact solutions, exact answers. So what I mean by that would be something like this. And then this isn't an actual function. This is something I'm just drawing off the cuff here so we can understand the concept of a limit. So limit describes function behaviors around places that don't really exist, for lack of a better word. So for example, this is our function. I'm going to call this f of x. And we notice that we have this big gaping hole right in the middle of the graph of our function, right in the middle of the graph of f of x right there. Let's call that c. So we know that we can plug in any value of x other than c and get a function value. Like for example, if we plug in, I don't know, let's call this a. So if we have x equals a, we can tell graphically that f of a most definitely exists. Same thing if we had another one right here, if we plug in x equals b, and we can tell intuitively that f of b certainly exists as well, just like f of a does. But what about f of c? Does f of c exist? The answer is no. We don't have a function value when x is equal to c, so this value does not exist. But what would it be? I mean, theoretically, what would it be if c did have a function value? What would we expect it to be? So it's pretty easy to see graphically. We would expect it to fill the hole. We know f of c doesn't exist, but what if it did? If f of c exists, we would expect the function to fall right around this value, fill the hole. And that's what a limit really does. That's why a limit is useful. Limit describes function behavior in situations like this and many others where we don't have definitive definitions of a particular point, but we do want to analyze the behavior that occurs around that point. Let's say we have the limit, and then this is the conventional notation for limits. I shouldn't even say conventional. This is the across the board only way of describing limits. This is the way we use notation to describe a limit all the time. So a limit looks like this. It's going to be the limit as x approaches a certain value. I'm going to leave that blank for now. And then we put the function right there. Our function is f of x. And then what value are we concerned with? So we have this big gaping hole in the function that occurs whenever x is equal to c. So what that means is we're interested in the function value occurring around the place where x is equal to c. So we have the limit as x approaches c. So I kind of just want to go through this notation and then read it to you. So the way this reads would be the limit as x approaches c of f of x. And for purposes of this video, I think I'm going to put some arbitrary points on my y-axis to have a better understanding of our function behavior. Not just around the point, but just in general. All right, these are completely random, by the way. Let's say we have 1, 2, 3 would be our first y value for this first point. Then we have 3, and then I'm going to put the 3 right there. We have 1 and then 2 and then 3. Oops, sorry, my mistake. That's what happens when you have bad handwriting, and not only that, when you're trying to draw with a mouse instead of a drawing tablet. I usually have a drawing tablet, but that is not working at the moment, so I'm stuck using my mouse for drawing. My apologies. My handwriting and my drawing will be even worse than usual. So we have y equals 1, y equals 2, y equals 3. Then we have 4, and we have 5, and we have 6. So we know that if we plug in a, x equals a, f of a is equal to 3. We know that if we plug in b, we get 6 because f of b is clearly equal to 6. But what if we plug in c, what do we get? Well, we get an undefined value. So maybe another way of phrasing that would be, what do we expect to get? So if we fill the hole, we can see that we would expect f of c to be 4. So let's go ahead and fill the hole. We would say that this limit is equal to 4. So I want to read this to you. The limit as x approaches c of f of x equals 4. And that's mainly what the concept of a limit is in this context. But I want to introduce maybe another context and a different kind of discontinuity. And that's another thing. Before we even continue talking about limits, I'm sorry for kind of jumping around here, but I really want to talk about something that's extremely important before we even get into the more advanced topics in calculus, even for a preview purpose. I want to talk about continuity and discontinuity. So what is continuity first? We're going to start just with continuity. So continuity kind of looks like the word continue. So from a math standpoint, from a function standpoint, what can we interpret this as possibly meaning? So the definition of continuity is a function's ability to continue along a particular domain. So for example, if the domain is all real numbers for a function, and this is just going to be a generic function, I'm going to put arrowheads on each side just to indicate that it goes on forever and ever in both x directions, in the negative x and in the positive x. So what is continuity in this context? Continuity, like I said, is just a function's tendency to have definite values at every single point in a particular rate or in a particular domain, otherwise known as a particular interval. So in this case, we would say that this function is continuous on all real numbers, because we don't have any breaks in the graph, we don't have any holes, we don't have any asymptotes, any gaps. So that's a big indication that this function is continuous for all real numbers we can pick for x. And then we also have something called discontinuity, which you probably can infer that it is the opposite of continuity. So actually, I think I might want to use the same axis for this. I'm cheap and I'm lazy, so I'm going to use this one. So I'm going to introduce a new function that's not continuous for all real numbers. Let's say that we have, what would be a good one? Maybe natural log of x, which looks close to what I'm drawing right here, this blue curve. So this is natural log of x. Is this a continuous function for all real numbers, or is it discontinuous? We know it's discontinuous because we have a vertical asymptote right here whenever x is 0. We have a vertical asymptote at the vertical line, x equals 0. And not only that, we know that nothing occurs to the left of the line. It would be one thing if the function existed, something like this, but we know it does not. We know it stops cold right at this vertical asymptote. It does not move left of this line. It does not even touch this line. So our blue function, natural log of x, is certainly not continuous on all real numbers. So this would be discontinuous. We have a region of continuity, which would be everything to the right of the vertical line. We have a region of discontinuity, which would be everything to the left of the vertical line and also including the line itself. So continuity and discontinuity just describe circumstances in certain regions in which a function exhibits certain behavior. Let's maybe come up with another one real quick. I like the one I had before that had a gap in it. I think I'm going to bring something like that back into the mix. So let's say we have another generic function. Something that looks maybe kind of like a cubic or maybe like the sine or the cosine function. Could be either of those, but we're not really concerned with that at the moment. So this red function, we want to describe the continuity and the discontinuity of the red function. So if the hole was filled, if we did not have a gap right there, we could tell that our red function would be continuous for all real numbers, but unfortunately that is not the case. We can see that we have another pesky little x value for which our function is not defined. So that means our function is certainly not continuous on all real numbers. Our function has, it looks like, two intervals of continuity and one single point, not an interval, but a single point of discontinuity. So let's maybe label these real quick to get an intuitive sense of what's really going on algebraically in each of these functions. So I'm going to call the black one f of x. I'm going to call the blue one g of x. I'm going to call the red one h of x. So we know that f of x has continuity for all real numbers. F of x is continuous for all real numbers. And then we can say that our blue function, g of x, is not continuous for all real numbers. Why did I erase that? I don't know why I did that. So we can tell that the blue function, natural log of x, is not continuous for all real numbers. Let's define the interval of continuity and define the interval of discontinuity for our blue function, but I want to move this aside a bit. So our blue function for f of x, or sorry, g of x is our blue function. We can tell that we have an interval of continuity everywhere where x is greater than 0. We know that if we plug in 0 into the natural log function, we get an undefined value. So g of 0 is undefined. So we want to overwrite the interval of continuity for g of x. We could write it just like this. This is a pretty conventional notation. We would say that it's continuous for x values for which x is strictly greater than 0. That is our only interval of continuity for g of x. Now let's talk about h of x, our red function. So we can say that h of x has two intervals of continuity. It would be all the values for which x is less than c. And we can say that it's continuous for all the values for which x is greater than c as well. So we could maybe combine those two in a way. We could say that I think we should just stick with that conventional notation we used for g of x. We could say that x has to be either less than c or x has to be strictly greater than c. For our function I don't know why I keep saying that. For our function h of x to be continuous, we can have a continuous function for h of x for every single x value except x equals c. So these would be our two intervals of continuity for the function h of x. Now I'd like to do the exact same thing only for discontinuity. So what is the discontinuity for our black function for f of x? Well, it doesn't really have any discontinuity to speak of. It's perfectly continuous, has definitions for all values of x. So I think the way I want to describe that would be using the notation for an empty set. The 0 with the slash through it inside the curly braces. That's just the notation that means it's a set that includes nothing at all. The discontinuous set for f of x does not exist. There's nothing in that set because it is completely continuous for all x values. Let's do something similar for g of x. So for g of x, we can tell that our interval of discontinuity would be everywhere where x is at less than or equal to 0. Discontinuous when this condition is met. And then we'll do the same thing for our red function for h of x. Now, what is our behavior like for h of x regarding its discontinuity? We can tell that except for the value of c right here, it is an absolutely continuous function for all values of x. So one way we could describe that, we could use notation. And actually, I think the best notation to use for this one, for the discontinuity, would be x is equal to c. So when this condition is true, h of x is discontinuous. H of x is discontinuous whenever our x value is equal to c. So continuity and discontinuity are extremely indispensable, extremely important for us to understand the basics of how calculus works, not only visually, but also analytically, also graphically. We're going to be exploring those three methods of function analysis in this class, graphically, analytically, and algebraically. We have continuity, we have discontinuity. So like I said, I apologize for kind of jumping around. This video is kind of just off the cuff, not really planned all that well, but I want to maybe go back to some of the prerequisites that I feel are really necessary to understand calculus. And limits, it depends on who you ask. The concept of a limit could be a prerequisite for studying calculus. The reason I say might be is because some pre-calculus classes include limits in their curriculum. I never actually took pre-calculus myself. I kind of just studied it independently before jumping into AP Calculus in high school. But for our purposes, we want to maybe understand that the limit is taught in some pre-calculus classes, and then in other classes it's not taught until calculus. So it's a good idea to maybe understand what limits are. Even if your pre-calculus does go into limits, it's useful to review them before getting into calculus, because without limits, we're not going to be able to understand the next big main ideas of calculus, which are derivatives and integrals. And depending on who you ask, infinite series. You're not going to be able to understand any of that stuff without having a really solid understanding of what limits are and how to properly use them to solve complex problems. So I want to try maybe a few more examples of limits, make sure we have a good understanding of what they are. Let's say we have some function. Let's say we have f of x is equal to, what would be a good one? I think maybe 1 over x minus 2. So I want to just identify that this f of x is completely independent from this one. And in fact, I think I'm just going to remove this one outright. I don't want to get f of x confused with the other f of x. So this is our function. Let's sketch it. So we know that without the -2 there, our basic parent function would just be 1 over x. And we know exactly how to draw 1 over x. The real question is, what does this -2 do to the way the graph looks? So we know that this is going to be a shift 2 units to the right. So we're going to go x is 1, x is 2, and then under normal circumstances, our asymptotes would be x equals 0 and y equals 0. Under these new circumstances we're faced with, our horizontal asymptote's not going to change. The vertical asymptote, however, is definitely going to change. It's going to move 2 places to the right just as the function itself does, just as the curve of f of x does. So this is our new vertical asymptote. Our function is going to look like this. So let's use the graph to help us figure out the limit as x approaches 2 of our function, the limit as x approaches 2 of f of x. So this one is kind of tricky. It doesn't really fit in with that last limit problem we did where we had just one gaping hole in the function and it's pretty clear to see where it should be, where to fill the hole. This one, it's trickier than the last one because we can tell that we have function behavior going in 2 different directions. We can tell that if we approach from this side, our y value is going to increase. We can tell that if we approach from this side, our y value is going to decrease. So it doesn't really make much sense to use this context, this notation of a limit. So what we might want to do instead would be to split it up into 2 different limits. We're going to have the limit as x approaches 2 from the negative side. So that means we're going to start from the left and work our way to the right. Another way of saying this would be x approaches 2 from below. So we can tell that if we start at -infinity, we work our way right and right and right, we can tell that our y value is going to decrease. So the limit as x approaches -2 from below is going to be the end behavior. We can tell that the end behavior indicates that our function approaches -infinity. So that's all limits do. Limits indicate the end behavior of a function or just behavior around discontinuity, like an asymptote, like a hole in the graph, for example. So now we're going to have another one. We're going to have one as x approaches 2 from above or from the right. Both are correct, technically, of our function of f of x. Kind of squeezing it in there, don't have much room to write. So we can tell that if we start from the right side and work our way to the left, as x gets smaller and smaller and smaller, y is going to get bigger and bigger and bigger. Y is going to approach positive infinity. So that is the value of our limit as x approaches +2 from above or from the right side. So aside from that, it's really important for us to have a really good, really solid understanding of all of our tools from pre-calculus and from trig and from algebra and geometry to help us simplify things in order to make calculus operations not only easier, but understandable. We want to use these tools to help us understand what's really going on in a calculus problem. We don't want to think about calculus operations as being algorithmic in nature. We don't want to think of it as just a series of steps like long division. We want to understand what's actually happening at the most basic level algebraically, because only then will we be able to have a strong enough understanding to use it to solve complex problems. We don't want to just memorize steps. We want to understand the process so that way we'll be able to derive the steps ourselves, which is far more helpful in an exam situation. So included in that would be, of course, all of our algebra tools. Being able to factor quadratics is extremely, extremely important. If you're ever sitting in an algebra class, bored out of your mind, wondering why you're supposed to be learning this, it's because if you want to study medicine or engineering or science or economics or anything that's extensively mathematics related, you're going to need calculus and you're going to need how to factor this in order to effectively use the calculus tools to solve problems. So factoring is just one of the many things you're going to want to have learned. Another thing would be polynomial long division and polynomial synthetic division. So it would be like, I want to just modify this f of x. So let's say we have something like this. So the operations in calculus are much more difficult when we're faced with something like this. So what we want to do instead is we want to use polynomial long division to break it up into something else. And I don't know what this is right off the bat, but I'm going to just generalize it like this. Then we have some kind of a remainder. Oops. So in general, what we have over here to the right of the equal sign is much, much more easy to work with in calculus than what's to the left. It's always in our best interest to be able to break up a more complex problem in smaller and smaller pieces that can each be solved individually. I don't know if many of you have had any experience with computer science, any experience with coding, but this is a concept that also extends into coding quite a bit. It's the concept of modularity. Modularity is the process of breaking up a really big monolithic problem, a really big complicated problem that looks impossible and scary, into more smaller problems that are easier to solve individually. Breaking up a big problem into small pieces that we can do individually is a really common theme in computer science. And it also applies in calculus quite a bit, quite often. That is modularity. And modularity is the reason why we want to know polynomial long division and polynomial synthetic division very, very well. Another thing that we're going to want to have mastered would be the basic area formulas. And I don't want to give away, you know what, actually, maybe I do want to spoil the surprise. I feel like we should get into the other main ideas of calculus because it would help us understand these prerequisites just a little more clearly. So we talked about limits. Let's talk about the next main idea of calculus. It would help if I can spell the words I'm trying to write. And I apologize again for jumping around, but I feel like this order is fairly strategic in helping us understand these concepts as best as we can. So derivatives are considered to be probably the second main idea of calculus, depending on who you ask. Limits would be the first, derivatives would be the second. So what is a derivative? A derivative is the rate of change of a particular function. It's the slope. And we're pretty good at finding slopes by this point. y2 minus y1 over x2 minus x1. Perfect. But what the heck are you supposed to do when you're trying to find the curve of something like this, maybe e to the x? How the heck do you find the slope of e to the x? Well, I mean, I guess we could maybe approximate it. We can maybe make a pretty good guess. So we have a point there. We have another intersection point there. So it would make a really good guess that this would be the slope of the curve. This would be the rate of change of e to the x. But it's not good enough. We want to have not an answer that's just an approximation. We want to have the exact slope of the curve. Easier said than done, right? Seems impossible, but it actually is possible. So let's pick values that are closer together. Let's pick a point right here. This is A. Another point right here, which is B. So let's ask ourselves what happens as B gets closer and closer and closer to point A. I'm kind of a visual learner, so I'm going to color code this. And it's worth mentioning, the calculus is a very, very visual art, especially when we get into the concept of integration. So it's always a good idea to have strategic ways of labeling your notes, maybe color coding them the way I do, to help us understand the concepts easier and make it easier to review your notes and understand what the heck is going on in a problem you did maybe 2 days ago, maybe a week ago. You want to give yourself really detailed notes just in case you go back and study, you're not completely lost, you're not completely wondering what you did in this situation. So let's draw what this line would look like as best as I can. All right, not too bad. Let's maybe make a third B that's closer to A. And I want to draw another line connecting the 2 points, if possible. So out of these 3 lines, or actually, yeah, out of these 3 lines, which would have the closest value to the rate of change at the point x equals a? Well, it would have to be the red one. It's the red one because we can see that these 2 points are closest together, and it would generate the slope that is closest to the actual slope at the point x equals a. So these are called secant lines, and they're not exactly related to the concept of secant function from trigonometry. They're not really related to the secant function, but we call these 3 lines secant lines when they're connected by 2 points. Now let's see what the actual slope would be. Instead of drawing another secant line, let's draw a tangent line. So the tangent line is a line that only touches the line in 1 point. So we can see that these 3 lines touch the function in 2 different points. A tangent line only touches the function in 1 point. So let's see here. I would say that this is a really good example of a tangent line because it only touches the curve in 1 point. So we can say that this new line that I made, and I think I want to alter its appearance a bit so that it's distinguishable among the other lines. Yeah, this one. So we can see that this green line is much closer, if not identical, to the slope that we would expect of the function around the point x equals a. So it's important to know how to find derivatives because derivatives represent the rate of change, and we're living in a world where everything changes. Amounts of time change, amounts of money change, reactants in a chemical reaction change, things in our global economy change, things in weather patterns change, and greenhouse gases, everything changes. So it's a really good idea to understand how to visualize this change and how to make it contextually applicable to whatever you decide to study in your later life, be it economics or physics or engineering or anything like that. Derivatives just make this information more relatable to whatever we happen to be studying. That's all. And a derivative is just a rate of change. And we're not going to get into the nitty-gritty of what derivatives are, but I do want to give kind of a preview of how they work algebraically. And this is going to fall back on some prerequisite pre-calculus knowledge. So I don't know if you have taken pre-calculus, but if you have, there's a good chance that you've been introduced to something called the difference quotient. I want to make that a different color. Not feeling the green anymore. Difference quotient. What is a difference quotient? So algebraically, a difference quotient is a limit. Well, actually, if you see this in pre-calculus, chances are you won't see it as a limit. You'll see it as something without the limit. You'll see it as something like this. And what the heck is this thing? How is this useful? Well, this thing, along with a limit, helps us to find the slope of the tangent line of a particular curve. So let's say we just call this generalized function f of x equals e to the x because that's kind of what it looks like. So if you're seeing this at the beginning of a pre-calc class, you're not going to have a limit. But if you're taking this as part of a calculus class, we're going to have the limit as h approaches infinity. But in pre-calc, they usually use h. In calculus, they typically use delta x instead of h. And this video is getting kind of long. I don't want to get super into detail. I don't want to get into the nitty-gritty, but I do want to cover the basics. So in a calculus context, we would describe this as being the limit as delta x approaches 0. And why the heck is that? Why do we care about delta x approaching 0? Well, I'm so glad you asked. Let's take a look at these 3 lines. They look kind of like sticks of spaghetti sticking up in opposite directions. We can see that as b gets closer and closer to a, our line gets closer and closer to the actual slope. So let's say that this would be one value of x. Let's say this would be another value of x. And let's say the difference between our 2 x values is delta x. So our largest value of delta x would be this right here. Our smallest value of delta x would be this right here. But what if we were to bring delta x all the way down to 0? This isn't small enough. It is smaller than the rest of them, but it's not small enough for our purposes. So what we want to do is we want to get a delta x smaller and smaller and smaller. So theoretically, it would approach 0. Theoretically, we want 0 difference between a and b. So that's why we're taking the limit as delta x approaches 0. And I'm not going to get into this part in this video. Like I said, don't want to get into the nitty-gritty, but you will definitely be spending quite a bit of time with this when you take calculus. This is the limit definition of the derivative, and To be honest, we have much easier tools to find derivatives, but you have to crawl before you can walk. We have to learn this to understand exactly intuitively why these calculus tools behave the way they do, instead of just memorizing steps. Because if you memorize steps, you make mistakes. Humans are not perfect. My memory is certainly not perfect, as I'm sure you're well aware by now. It's better to have a really good understanding of the core concepts behind these things instead of just memorizing steps, because steps are fallible. Human memory is fallible, but intuition and understanding is completely infallible. So it's really a good idea to have an understanding of the core concepts themselves, because it makes everything else just so much easier. So those are derivatives. Now let's move on to what's considered to be the third main idea of calculus, the integral. Integration. So integration is the process of finding an integral. So what the heck is an integral? An integral, well, we know that the derivative tells us the slope of a function. It tells us the slope of the tangent line, the rate of change of a particular function. An integral tells us the accumulation of a particular function. So let's say we have a situation like this, and I'm going to draw just another generic function. Let's say we wanted to find the area under the curve between two x values, calling the first one a, and we'll call the second x value b. We're interested in finding the area under the curve between a and b. And you might be wondering why the heck we want to do that. Well, it's because if we find the area under the curve, it gives us so much information about a particular function. So for example, what if this curve right here describes the rate of change at which a car is moving? What if the curve describes a car's speedometer in miles per hour? What if we're given the graph of the speedometer and we want to know how far a car travels between time equals a and then time equals b? What if we want the distance traveled? So we know between these two particular endpoints, we can see that we travel this distance, and then we travel this distance right here, and then we travel this one, and then that one, and then this, and then that. So if we were to get an estimation for this area under the curve between A and B, it tells us how far our car travels in this time interval. It helps us going from miles per hour to just miles. And it's kind of interesting because integration is actually the opposite of differentiation. Integration is the opposite of taking the derivative. So differentiation is the process of taking the derivative. Integration is the process of taking the integral of a function. Integration and differentiation are opposites. The integral of a function is the opposite of the derivative of a function. And we see this two-sided dichotomy. I can't even talk today, I apologize. We see this dichotomy quite often in math. We remember that addition and subtraction are opposites. We remember that multiplication and division are opposites. We remember that exponentiation and logarithms are opposites as well. Derivatives and integrals are opposites. The rate of change of a function somehow algebraically is the opposite of the area under the curve of a function. So this is another example where we desperately need a limit to help us make sense of the problem at hand, to help us make sense of this problem of finding the area under the curve. Because as we can see, the first thing I did was dreadful. This is a horrible approximation. And even with the rectangles, it's not all that much better. We can tell that this is still very far from the actual 100% perfect area under the curve between A and B. So what happens if we were to take more rectangles? What if we were to cram more rectangles into this interval and make them smaller? Let's give it a try, shall we? Whoops. So we can see that as we add more rectangles, our area gets closer and closer to the real thing. What if we were to enclose an infinite number of rectangles? And for those of you with OCD, I apologize for not doing this next part right here. I have a bit of OCD myself, so what I'm going to do is bring B a little bit closer. That's only because I'm too lazy to draw the rest of the rectangles. This is a mix of OCD and laziness, something that I'm known very well for in my teaching. So A and B are right here. these rectangles represent an approximation of the area under the curve between A and B. So let's see what happens if we were to add an infinite number of rectangles. What if instead of having a width like this, what if every rectangle had a width theoretically of just 0, or as small as we can get, as close as we can get to 0? If we were to make all of these as close as we can to 0, we would have an infinite number of rectangles. So the formal definition of an integral, but I want to introduce the notation first. So an integral looks like this. You may have seen this symbol before. It's pretty common in math. This would be the definite integral going from a to b of our function f of x times dx. And I'm not really going to explain in this video where the dx comes from. I don't want to spoil the surprise, but when you get into integration, it will become very clear where this dx comes from. F of x is just the function. This is the definite integral of the function. So an integral tells us the area under the curve starting with a, ending with b. So the formal definition of a definite integral, I did not give myself enough room. Forgive me for that, please. So the formal definition of a definite integral is the following. It is the limit as n approaches infinity of the sum going from I equals 1 to n of f of c sub I times delta x. So it's pretty scary looking. There's a lot of stuff going on here. So let's take it down bit by bit and understand what each of these things are doing to our function, doing to f of x. So this limit as x approaches infinity, n is a number of rectangles. So let's say we have a really, really bad approximation for the area. Let's say we have something like this. 3 rectangles. Really rough, not a really good area approximation at all. 3 rectangles is not very good. So instead of having n equals 3 rectangles, we're going to have n equals an infinite number of rectangles. We're going to cram an infinite number of rectangles under the curve in this interval. So n being the number of rectangles, we're going to keep bringing that closer and closer to infinity. So that's what this limit means. We're taking the limit as the number of rectangles reaches infinity. Then I apologize for my allergies. I feel like I'm allergic to everything, and it is annoying and a little scary, and I don't know what to do. So we take the limit as the number of rectangles approaches infinity. And then this Greek letter sigma right here, this big E looking thing, this is a capital sigma. It's a Greek letter. It just means we're taking the sum of f of c sub I. So f is our function. C sub I is just any generic point. So if we pick c sub I to be right here, f of c sub I would be, let me maybe use a different color. F of c sub I would be this point right here. F of c sub I. So if we pick c sub I to be right here, f of c sub I would be this point. If we pick c sub I to be right here, f of c sub I would be right here. So that's all c sub I really is. We're just picking a generic value of x and finding the height of the rectangle that we draw whenever c of I is this particular value. So we're adding together all of these rectangles, but then what the heck does delta x do? We know that delta x is just a difference in x. This has a ton of Greek letters. We have sigma, we have delta, there's going to be many more to come. So we know that delta is the Greek letter we use to symbolize change. So delta x is going to be the expression we use to symbolize the change in x values. And let's get a really good sense of what that means graphically, because calculus is a visual art. We want to have pictures to help us understand complex problems, because it just makes it that much easier to learn and understand the concepts. So I'm going to pick this middle rectangle. This middle rectangle has a width of delta x. So all this is saying is we're adding more and more and more rectangles. We're adding an infinite number of rectangles. We're going to be adding them all together, and we're going to be multiplying every rectangle by the base, because we know that the area of a rectangle is going to be the base times the height. So we're taking one rectangle. The area of one rectangle is base times height. We're going to do that for every single rectangle. So the sum just means we're adding together base times height for the first one. We're going to add base times height for the second one. We're going to add base times height for the third one. We're going to add base times height for every single skinny rectangle we draw under the curve. So this is kind of scary looking, but once you break it down bit by bit, it becomes a lot easier to understand why this is the way it is, why the formal definition of the integral is this big scary thing. And kind of like with derivatives, there are much, much easier ways to calculate the integral. I'm not going to spoil the surprise for you when you get into the integration part of our calculus class. You'll see very clearly why this is what it is, and you'll understand the tools we use kind of like as a shortcut to make integration easier. We're not going to be using this for very long. This is just a tool we use to help us understand the idea. Like I said, we don't want to remember steps because human memory is fallible. We don't want to memorize the steps, we just want to memorize the process, because if we understand the process really, really well, we can derive the steps ourselves using pictures, using notation, and using our knowledge of these core concepts. It just makes it much easier to retain the information and use it to solve problems. So that is the concept of limits. That's integrals we've covered, and we've also done derivatives. And then the third concept would be infinite series, which I'm not really going to get that much into, but it is very much related to integrals. So a series looks like this. We always start with the Greek letter sigma, I equals 1, and then an infinite series would be adding together an infinite number of numbers. Let's say we're adding together 1 plus 2 plus 3 plus 4, and the numbers never, never end. And you might be wondering, well, how the heck is it even possible to add together an infinite number of numbers? It just doesn't make sense. And you would be right. In certain circumstances, it does not make sense. In other circumstances, it does, algebraically. So if the numbers keep getting bigger, we can't find the sum, it's impossible. But what if there were certain conditions? What if the numbers were to get smaller? What I mean by that is, what if we had maybe something like a half plus a third plus a fourth? Now, this might be possible to solve. It might be impossible to solve. It might be possible or impossible to find this sum. But in some cases, an infinite series is possible to add together. In certain situations, it is possible to add together an infinite number of numbers, but there are a list of very, very strict restrictions that must be upheld in order for us to be able to even find the sum. And I don't want to spoil the surprise, but this is just a brief introduction to our fourth main idea of calculus, which is infinite series. Excuse me. We know what a series is. A series is just adding together a bunch of things. We know what infinity means. It just means a never-ending quantity. So an infinite series is adding together a list of numbers that never, ever end. And that's it. That's all we need to know for calculus. And I kind of took a segue. I kind of went into the integration and infinite series talk before continuing the prerequisites. And I kind of maybe just want to finish that. So it's important to know geometry. And you might be wondering, well, how the heck is geometry going to help us with calculus? Because we can see that in our integration unit, area is of the utmost importance. Integrals tell us the area under the curve. And there are going to be certain situations where we might not be able to find the integral, but we can find other pieces of important information about our function. So like, what if we had, for example, I sound like a Valley girl saying like all the time. What if, for example, we have the graph of a circle with the radius of 1? Simple circle. No matter how simple it is, there's a guarantee that I'm going to screw it up. So brace yourself for that. So consider we have just a basic circle with a radius of 1. And we're interested in the integral of this function. So what is the function representation? What is the equation for a circle? The equation of a circle looks like this. We have y is equal to the square root of radius squared minus x squared. This is our explicit formula for graphing a circle. And this only graphs the top half. We know that a circle fails our vertical line test, so this only graphs the top half of the circle. And I'm too lazy to cover up the bottom half, so just pretend like it's not even there. So what if we have something we can't integrate, but we still want to find the area under the curve? Let's say we wanted to find, for example, this area that I'm going to draw. This horrible, messy area. So what I want you to do is just pretend like it's perfect. Pretend there are no gaps right here. Pretend there's nothing going outside the curve. Pretend it's just perfect. So what if we wanted to find the integral of this function, but we can't do it? What if the integral is too hard? So this is where geometry helps us out. This is in case we have something that's impossible to integrate, because let's face it, they do exist. It's possible to find the derivative of everything, but it's impossible to find the integral of everything. There are some things that just do not integrate that you would have to use a calculator for. So what if we wanted to find the integral, I think I'll make that a little bit neater. Actually, no, I don't think you should, because if I make things neat, you'll expect it to be like that all the time. And I feel bad setting expectations so high. I want to keep the bar low and never raise it, never exceed it. So what if we wanted to find the definite integral, actually maybe going from -1 to 1? I set the bar low early on, for my sake and for yours. So let's say we wanted to find the definite integral of our function. And instead of r squared generalized, I'm going to replace r with 1 because we know for sure that the radius has to be 1. So we have 1 minus x squared underneath the radical. This is our explicit formula. And again, we're not going to get into dx, what dx does. But what if we wanted to find this integral and we have no idea how to do it? Well, we know that the area under the curve is the same thing as the integral. So what is this blue area? Again, we're pretending I didn't mess it up. We're pretending it's perfect. So what would this perfect area of the top half of the circle be? Well, we know area is pi r squared. R is 1, so the area would be pi for the entire circle. For the top half of the circle, it would be pi over 2. Hey, look at that. We did calculus without actually doing calculus. We found the answer without integrating. We cheated. We used geometry as a crutch, to cheat our way through this class. So this is why geometry is important. This is why it's really important to understand the area under the curve of a particular function. And it also helps to understand those classical geometry applications as well. Area of a circle, area of a rectangle, parallelogram, all those things. It's important to have a really, really good understanding of area. So, and let's see, I think that might be everything. I know if I end this video, I'm going to suddenly remember something I forgot to talk about. So let me think for a second. I'll pause this while I think. So in addition to the tools we've already been discussing from algebra and geometry and pre-calc, there are some more that we want to have a really, really good understanding of. We want to understand logarithmic functions and exponential functions. We want to understand things that look like this, y equals a to the x power, where a could be any real number. A could even possibly be another function. So the most common one we use would be a equals e, where this would be the most common exponential function we use in calculus. And you might be wondering, you might be sitting in Algebra 2 wondering why e is important. It's just some weird irrational constant. We know why pi is important. It pertains to circles. In calculus, I don't want to spoil the surprise, but in calculus, you'll learn why e is such a cool number. It has all of these properties in calculus that make it relevant, kind of like how circles make pi relevant. Like I said, I don't want to spoil the surprise, but we're going to be covering topics like this one. We're going to be doing calculus operations on exponential functions like this. We're also going to be doing some calculus operations on functions like this below. Where a could be anything. So the most common type of a logarithm we use in calculus would be natural log of x. And I apologize if you have OCD. I apologize for typing some of this stuff and then writing the other stuff. I am deeply ashamed. I apologize from the bottom of my heart for that, but I am very lazy, so that's why I'm doing this the way I'm doing it. So this would be probably the most common logarithm we encounter in calculus. We're going to be doing derivatives. We're going to be doing integrals of logs all the time. We're going to be doing derivatives and integrals of logarithmic functions constantly. So it's a really good idea to understand how to go from one form to the other. Or actually, hang on, that's not correct. This one would be, these two are inverses of each other. So it's a really, really good idea to understand inverses, to understand how we get from this to the bottom one, or go from the bottom one to this one. And it's also a super good idea to understand the domain and the range, because continuity and discontinuity are a major idea in calculus. We want to have a really good understanding of continuity and discontinuity and the domain and the range of these functions for us to properly analyze their behavior using newly found calculus tools. And then I think probably the last thing we're going to want to make sure we're good on would be trig functions. So if you haven't really had Algebra 2 or pre-calc yet, chances are you'll know sine and cosine and tangent if you've taken geometry. We know SOHCAHTOA is a really good mnemonic device. I don't even know if I said the word mnemonic right, but it's the device we use to remember how to find the sine of a function, or sorry, not a function, the angle. How to find the sine of an angle, how to find the cosine of an angle, or how to find the tangent of an angle. So we're going to take things a step further. We're going to kick things up a notch. We're going to be finding sign of a function, and then more Greek letters. This is theta. Theta is just the identifier that's used the most commonly. I can't even talk. That did not make grammatical sense. Most commonly, theta is the most common identifier we use to identify an angle. Algebra uses a lot of x's and y's, a, b's, and c's. Trigonometry uses theta most often, but they also use a lot of alphas, and they also use a lot of betas as well. With theta being the most common. This is the Greek letter theta. This is the sine of angle theta. So we're going to be doing calculus operations on the sine function, on the cosine function, on the tangent function, and also on the reciprocal of functions as well. Cosecant of theta, cosecant function, and then the secant function, secant of theta, and then also our cotangent function, the cotangent of theta. We're going to be doing derivatives and integrals of all 6 of these functions. So it's a good idea to have all of the sine, cosine, and tangent, and cosecant, and secant, and cotangent values memorized for all of our most widely used angles in the unit circle. So what I mean by that would be pi over 6, pi over 3, pi over 4, pi over 2, pi, 2 pi, and all the multiples of all of these. Before you study calculus, you're really going to want to have all of these memorized. If someone asks you what is the cosecant, for example, of 11 pi over 6, you're going to want to have it memorized to the point where you can just rattle it off without really thinking about it. So cosecant of 11 pi over 6 is the reciprocal of sine. So what is the sine of 11 pi over 6? Well, that would be 1/2. No, sorry, negative 1/2. I lied. Sine of 11 pi over 6 is negative 1/2. So then what is the cosecant? Cosecant is the reciprocal of sine. So it would have to be the reciprocal of negative 1/2, which is negative 2. So the way I solve these in my head is I just visualize this triangle. I think to myself, well, if our angle is 11 pi over 6, that would be just 1 pi over 6 short of an entire circle. So if this right here is an entire circle, this right here is 2 pi, this is 12 pi over 6, then 11 pi over 6 is going to be 1 multiple of pi over 6 less than the full circle. 1 multiple of pi over 6 less than 12 pi over 6. So I just visualize what this triangle looks like, and I just make the connection that this has to be negative 1/2 because we have a y value of negative 1. We have an r value of 2. We have an x value of square root of 3 in this particular reference triangle. So we're going to want to have all 6 of these trig functions memorized for all of the angles we use in the unit circle. All the multiples of these between 0 and 2 pi, between 0 and 360 degrees. And you're also going to want to know how to properly and efficiently use trig identities. And trig identities are important because we're often going to be asked how to do integrals of really nasty looking things. Something like this, perhaps. Maybe we're going from negative pi over 2 to maybe 2 pi, who knows. But we're going to want to be able to understand trig identities really well because trig identities help us take these really complex problems and make them into much simpler and easier problems, especially with integrals. Trig identities make integrals from nightmares into things that we can do in our sleep without breaking a sweat. They just make problems much easier and simpler and smaller to solve and faster too. And then I think there's just one more thing that I want to cover as a prerequisite for studying calculus. That would be the concept of, well, it is kind of related to polynomial long division and polynomial synthetic division, but it's not exactly the same. That would be the concept of partial fractions decomposition. So I teach calculus. I've taught calculus 3 times. I'm currently teaching it for the 4th time. I've also taught pre-calc quite a bit as well. And in my experience, this isn't really taught in pre-calculus as much as it used to be. Like I said, I never took pre-calc myself, but in my experience, maybe a decade, maybe 2 decades ago, this was commonly taught in pre-calc, but it's not really taught that much anymore. But it is still very important. What is it exactly? Well, partial fractions decomposition involves taking some expression. I'm going to just maybe generalize this. Taking some complex rational expression and then breaking it down into smaller, more manageable parts. So what if we could break it up into something like this? And disclaimer, what I'm doing is total nonsense right now. This is not actually equal to what's on the left. The right and the left are not equal. That's just my disclaimer. What if we could break things up into smaller, easier chunks? Something like this. And like I said, this is far from being accurate. What's to the left is nowhere near being equal to what's on the right of the equal sign. So I'm just going to erase this and maybe just give a quick explanation on this. So we're breaking up one big monolithic rational expression into several smaller expressions that are much easier to integrate. So whenever we have an integral, we can always break up an integral into much smaller pieces. So for example, if we know that we have an integral of x squared plus 5x plus 3, an integral can be broken up into small pieces. We could say that this is the integral of x squared getting its own integral plus the integral of 5x. 5x also gets its own integral, and then 3 gets its very own integral as well. It's like being on the Oprah Winfrey show. You get an integral, you get an integral, you get an integral. Everything gets its own integral, which is one of the most useful tools we use when we're studying integrals and studying calculus in general. Helps us break a problem up into smaller pieces. So you can do that with I can't talk, I'm sorry. We can do that with some big rational function like this. This one is a nightmare. I feel sorry for anyone who has to integrate something like this, for anyone who has to take the integral of some crazy, scary looking thing like this. But we use partial fractions decomposition to break it up into separate fractions that can be integrated separately. I don't want to do this one. I'd much rather do these three. Makes life that much easier. So that's about it. That's about as far as I wanted to get into our brief introduction of calculus. We talked about what the different calculus operations are, limits, derivatives, integrals, and a brief explanation of infinite series. We also got into the prerequisites we want to have down cold for us to be able to effectively understand calculus and to use the tools to maximum potential to solve complex problems. I hope you found this useful, and I hope to see you in one of my calculus classes one of these days. Peace out.